Welcome everyone to the Solving Functions Crime Show, where Detective Rahma takes you on a journey to solve today's most trending functions. We air weekly at Mondays, 9 p.m. Eastern Time. Watch as we uncover the mysteries of each function of the week until we're able to graph the whole entire thing. On today's episode, we have this function right here. From what we can see, this is a rational function. Time to uncover what else. Come on, detectives. Clue is to figure out the asymptotes and the domain and the range of this function. So first, with the vertical asymptote. In this function, we can see that we must solve for the vertical asymptote. We must set the denominator to 0. In this case, we set x plus 2 is equal to 0. Then we must solve for x, which we figure out is negative 2. Therefore, the vertical asymptote is that x equals minus 2. Now we must solve for the horizontal asymptote. However, when we see this function, we can see that the degree of the denominator is less than the degree of the numerator. The degree of the numerator is 2, and the degree of the denominator is 1. We have made two more discoveries. The horizontal asymptote does not exist, and this function has an oblique asymptote. Now, in order to solve for this oblique asymptote, we must take the 0 of the denominator and use that in the synthetic division of y equals x squared minus 3 divided by x plus 2. So we must put the synthetic division table with negative 2 on this side and the coefficients of each of the equation on the top over here. The synthetic division process requires to bring down the first coefficient from the numerator and multiplying it by the next coefficient and then further adding it together. So as you can see here, we have brought down 1. We will multiply that by negative 2, negative 2. Negative 2 plus 0 is negative 2. Negative 2 times negative 2 is 4. And negative 3 plus 4 is 1. That is the remainder of our oblique asymptote synthetic division. And therefore, our equation using the coefficients 1 and negative 2 is y equals 1x minus 2, rearranged to y equals x minus 2. Now let's solve for a domain and range of a rational function. The domain of a rational function are all the values of x which the denominator is different from 0. To find the excluded value in the domain of the function, we equate the denominator to 0 and solve for x. In this case, we solve that x is negative 2, and therefore x is all real numbers from negative infinity to negative 2, union negative 2 to infinity. The range of the function is the same as the domain of the inverse function. So to find the range of the function, we must interchange the x and y values and then solve for y. Multiply both sides by x plus 2 and then simplify. Next, we must find the discriminant for which this equation is greater than or equal to 0. We find that y is greater than or equal to both negative 2 and less than or equal to negative 6. Therefore, the range is written in interval notation as y is all numbers, negative infinity to negative 6, union negative 2 to negative infinity. Now, let's put these points on our graph. We're on a roll and we've solved the first step of our case. Let's put into the graphing calculator to see how our function looks so far. And would you look at that? We're one step closer to solving our function. Let's continue to look for more clues. Our next clue is to find the intervals of increase and the maximum and minimum points. The intervals where a function is increasing or decreasing correspond to the intervals where its derivative is positive or negative. Here we have a function where we can see the points where it's increasing and the points where it is decreasing. Doesn't this make you quite happy? Here's a little joke for you. Buzz Lightyear is doing calculus. On which interval is f at x increasing? To infinity and beyond. Now, time to start with finding our first derivative. We take our original function and we use, because it is a rational function, we use the quotient rule, which is the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. That may sound like a mouthful, but it's really easy. As you can see here, we have the derivative of the top, which is 2x, times the bottom, which is x plus 2, minus the derivative of the bottom, which is 1, and times the top, x squared minus 3, all over x plus 2 squared. We simplify this, and we further simplify it to give us our final first derivative of x squared plus 4x plus 3 all over x plus 2 squared. Now it's time to find our critical numbers. Time to find our zeros and our restrictions for this derivative. We must calculate critical numbers to find when the function increases and decreases. Critical numbers are numbers that make the derivative of the expression equal to 0 and is neither minimum or maximum point. Therefore, we need to take the derivative of our expression and set it to 0 in order to solve and factor for x plus 3, x plus 1, which is equal to x equals -3 and x equals -1. As you can see, we've solved for the two zeros and we find that these are equal to x equals 3 and x equals -1. But based on our synthetic division from earlier and based on our domain, we already know that there is a restriction on x equals -2, and therefore this is also a CN. So our three critical numbers are -3, -2, and -1. Now let's make our interval chart. Here it is. As you can see, we have our three critical numbers, -3, -2, and -1, and it is arranged as seen on the number chart. We have our first from -infinity to -3, -3 to -1, -2 to -1, and -1 to positive infinity. We take a number in between -infinity and in between -infinity and -3, and we input that into f prime x, or our derivative. For instance, if we put in -4, we would get a positive answer if we substitute it into our x value. In the same way, we take a value in between -3 and -2, for example, -2.5. Another one here, -2 to -1, -1.5, and for -1 to positive infinity, we can do almost any number that is above -1, for example, 10. Once we input these values into our derivative, we can find that in this case it is positive, in this case it is negative, negative, and then positive, and from there we can determine that our function is increasing, decreasing, decreasing, and then increasing. Can you see where the maximum and minimum points are? If you can't, let me point them out for you. Over here we have our maximum point, and over here we will have our minimum point. Increasing is x's all real numbers from -8 to -3, and again from -1 to positive infinity. And it is decreasing from x's all real numbers to -3, -2, and again from -2 to -1. It's time to find our points of maximum and minimum. Again, we have our original function, and we take, to find our local maximum point, we input our interval that we have found, our critical number, -3, and input that into the x value in order to solve for -6. So our final is -3, -6. To solve for our local minimum point, we input -1 into the equation, the original equation. We solve to have -2. And as you can see, we find that the maximum is at -3, -6, and that the minimum is at -1, -2. Again, we have done this by looking at our interval chart and looking as to which critical numbers are associated with the arrows pointing either up or down, max or min. Here's our graph again, detectives. Let's see what we've found with our new clue. With this clue, we found where our max and minimum point is based on our interval chart and where it is increasing and decreasing. Let's plot these points down. There they are. As you can see, they align with our asymptotes, and we know over here that we are increasing and over here that we are decreasing. So our function, because we know it is an oblique asymptote, will look something like this and something like this. Great job! Now for our next and final clue, clue 3, the concavity and the inflection points of our function. In order to find this, we must find our second derivative. Again, we use the quotient rule in order to find this derivative for our second derivative based on our first derivative. Again, to refresher, the quotient rule is the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. So as you can see here, we have the derivative of the top, which is 2x plus 4, times the bottom, which is x plus 2 squared. Then we have the derivative of the bottom, which is 2x plus 1 to the power of 1, because 2 minus 1 using constant rule, times 1, and then we multiply that by the top, all over the bottom squared. Next, we can start to simplify. We can take away this 2 and cancel out this as well as canceling out to get the power of 3. Now if you see how we did this, we canceled out these 3 as they can be simplified. Now we can solve by multiplying using FOIL and multiplication in order to get our long factorable equation here. We can simplify this in order to find their second derivative as 2 over x plus 2 to the power of 3. This is pretty simple for something that looks very long. Now it's time to make a concavity chart based on the second derivative that we have found. As you can see here, this is the second derivative, but if you may notice, in order to find the point of inflection, we must solve for x. However, the point of inflection in this case does not exist because we are unable to solve for x. However, we can assume that x is equal to -2 as a possible point of inflection because we do not have a real point of inflection. We must make assumptions that x equals -2. And if you don't understand, this is because we cannot solve for x, because in order to find the point of inflection, we must solve x plus 2 over, we must solve this rational function to 0. And if we were to solve it, we know that we would have to multiply the denominator by 0, which would just equal 0, and that wouldn't work. Therefore, we must use our assumed POI, which is x equals -2. Now we make our concavity chart with a value that is less than -2 and a value that is greater than -2. We input this value into our second derivative over here. Example, any value that is less than -2 can be -10, and any value that is more than -2 can be +10. We input these values to find that it would be negative and positive, and therefore it would be concave down and concave up. So concave up would be -2 to +infinity, and concave down would be -infinity to -2. Put this onto our chart detective, we found another clue. Voila! As you can see, concave down from -2 to -infinity, and concave up from -2 to +infinity. This looks just as we imagined. Well done! We are finished solving for our function, and we were able to properly graph it using the clues that we found together. Great job, detective! Now we can confidently say that this function is a case closed. Great job! And tune in again next week, Mondays at 9 p.m. Eastern Time for another episode of Solving Functions, where we solve the hottest and trending function of today.